Alright, so now let's do problem 6 from section 2.2. So this is similar to problem 4, except the picture is a little bit more complicated, but let's just go through it. So here we have a picture of a function. It's kind of a wacky looking function. There's all sorts of holes and jumps and weird squiggly things. And we're going to have to answer a bunch of questions about limits of this function. Okay, so let's get started. So part A says, let's look at the limit as x approaches -3 from the left of h of x. I guess I forgot to label again. This function is called h of x. Okay, that's what the red function is. Okay, so the limit as x approaches -3 from the left. So here's x equals -3 right here. So if you look at this function, there's a hole there. Can you see there's a little hole there in the function? So that means the function itself is not defined at x equals -3, but the limit as we approach -3 from the left, which means from this direction over here on the left side of the hole, as we approach that hole, it looks like the y value is getting close to 4. So that's what the answer is going to be. It's just going to be 4. Okay. So you approach from the left, follow it along like with your pencil, and you see where it goes, and it goes up to 4. Okay. Now, part B is the same question, except we want to look at it from the right. So part B says limit as x goes to -3. So now we're going from the right. Okay. So now let's do the same thing. We want to go this time from the other direction. Going up this curve, as we approach -3, the y value looks like it's still going to 4. Okay? And that makes sense because really this function is almost continuous except for this one little point that was removed. So the limit from the right is also 4. Okay? Alright. Okay, so now usually when you see a question that says from the left and then from the right, the third question is then, what's the overall limit? So the limit as x approaches -3 overall is, and now we don't even have to look at the picture because if the limit from the left and the right are the same, then that is also equal to the overall limit without any pluses or minuses. So that means if you go from any direction, no matter which way you come from, you always agree where you end up. And you end up at the y value of 4. So since the limit from the left and the limit from the right agree, then that's also the limit from all directions. In other words, the overall limit, the limit as x goes to -3, is equal to 4. Okay? Okay, good. All right. Now, okay, part D, they just ask, well, then what is just f of -3? Okay, so the limit from the left and the right are the same. The overall limit is equal to 4. What's the actual function itself equal to? Well, if you look at x equals -3 and you go up and see what's the value of the function at -3, there's no value because there's a hole there. That's what the whole purpose of drawing that little hole is. It means that there's no value of the function there. So even though the function is defined everywhere else, at that particular point it's not defined. So even though the limit's all equal 4, the value of the function itself does not exist. So it does not exist. Okay? And later when we learn about continuity, we learn that this hole is called a discontinuity. It represents a point where this function is not what's called continuous. And the reason it's not continuous is that the limit and the value are not the same. In particular, the limit is 4 and the value is non-existent. So that means it's not continuous there. Okay, you'll learn about that later on in chapter 2. Okay, now let's move on to a different part of the graph. We're going to look at stuff centered around x equals 0. Okay, so part E says, what's the limit as x approaches 0 from the left? direction. Oops. Somehow I switched to f's instead of h's. I'll just pretend that this f is an h and that this f is also an h. Okay. Sorry about that. Okay, so yeah, this h of x, we'll just say f of x. I just mislabeled it, but this should be h of negative 3, and this should be h of x. It doesn't really matter in this little example. Okay, so as we go towards 0 from the left in this function, that means we just go down the curve from the left until we hit x equals 0. And in this case, it's actually defined here at y equals 1. So this is 1. Okay. And then, not surprisingly, the next question is the limit as x goes to 0 from the positive direction of this function. Go back to the calling it what it's called, which is h. And in this case, we go from the right, you go down, and looks like you approach negative 1. Okay. Okay. All right. And then, since it approaches negative 1, okay. Oh, that's the answer to that one. Then part G then asks, what's the overall limit? Okay. So the overall limit, so remember the rule is that the overall limit, you look at the limit from the left and the limit from the right, and if they agree on the same thing, then that's the overall limit. But if they disagree, and in this case looks like they disagree, people from the left say the limit's 1, people from the right say the limit is negative 1. Since they disagree, then that means there is no overall limit. So the overall limit does not exist in this case. Okay. So you go from the left, you think it's 1. You go from the right, you think it's negative 1. You can't agree, so nobody wins. Okay. And then part H then asks, what's the value of the function? So H says, what's H of 0? Okay. So here we just say if you plug in x equals 0, where is this function colored in? Down here there's this open circle. I don't know if you can see that, but it's got black inside of it just because that's the color of the y-axis that's underneath it. So this is an open circle. Here's a closed circle. The closed circle is what the value of the function is. So here the value of function for x equals 0 is y equals 1. So the answer is 1. Okay. And then like I said earlier, since this is another example of something where the function is not continuous because the limit and the value are not the same. So later on you'll learn about continuity. Okay, all right, now let's get into the good stuff. Oh, actually, no, okay, let's move up to x equals 2, and then we'll deal with this x equals 5. What the heck's going on there? Okay, so let's see, go to part I. All right, so part I says the limit as x goes to 2 of h of x. Okay, so here's 2. Now notice it's not going from the left or the right, it's just cutting straight to the chase, saying what's the overall limit. Okay, so the limit as x goes to 2, well, we just know, so we'll just use the knowledge that we've been using before, which is saying that the overall limit is just the combined limits from the left and the right. So we just have to make sure that they're the same. If you're going from the left, looks like the limit approaches y equals 2. If you're going from the right, looks like the limit approaches 2 as well. Y equals 2. So, and you can see that it's almost like you can imagine these people are marching up the hill, these people are marching down the hill. Even though there's a hole right here, they're sort of both going to collide at this spot if you let them. So the limit from the left and the right are the same, so that means the overall limit does exist, and it equals that y value of 2. Okay? All right, and then now for part J, they want us to actually, I'll just write that over here because it's small. Part J, they want us to find what's actually h of 2. Well, h of 2, so once again, just asking for the value of the function. You plug in x equals 2, you go up. The function is not colored in there. There's a hole, so that just simply means it's not defined at that spot. So we just say it does not exist. So it does not exist. Okay. So once again, this was an example of a discontinuity, because the limit and the value are not the same. The limit's 2, but the value doesn't exist, so it's a discontinuity. And once again, you'll learn about that later. Okay, so now let's move on to part K. And this is where we want to look at this strange stuff going on here. Okay, so part K says, what's the limit as x approaches 5 from which side? From the right. Okay. Okay. All right, so let's see if you can see what I've drawn here. I'm not sure if my drawing is very good. If you want to see a better drawing, you should look in the book. I believe it's page 97. So basically what the drawing is, from the left, the picture is this wobbly function that just goes up and down, this oscillates back and forth, up and down and up and down. But the closer the x value gets to 5, the more quickly it goes up and down. So you get closer and closer, it's going really fast until finally it kind of, I don't know if you can see this, but I've drawn sort of a dot, dot, dot. That's what they draw in the book. That dot, dot, dot is to indicate that the closer you get to 5, the crazier it oscillates, and it sort of never stops oscillating in a crazy way. It's kind of hard to visualize, but it's basically saying, like, even if you're really, really close to 5, it's going to be still jumping back and forth a lot. So it's going to be going wild as close as you get to 5. Okay. Now from the right, what's happening, we're just moving along this nice simple arc, and we just go all the way until we get to x equals 5, and it looks like we actually hit the value 5, 3. So from the right, which is what we're looking for here, it's actually pretty uneventful. We just go down and we actually land here at x equals 5. So I think that part is actually, you can ignore all this wobbly stuff from the right and just say the limit from the right is just x equals 3, or y equals 3, because x equals 5, y equals 3. That's where this is going, right there. Okay. Okay, but now let's go back to this wobbly junk. That's the last part. Part L says the limit as x approaches 5 from the left of h of x. This is sort of, we have to describe what's going on, this phenomenon that we were just looking at. And so let me just repeat what I said. So from the left, the function goes up and down and up and down and up and down and up, down, up, down, up, down, up, down, like that. And the closer you get to 5, the crazier it is. Okay? So whenever something like this happens, where a function wobbles crazier and crazier the closer it gets to a certain x value, you don't really have to understand like how to visualize that so much as just knowing that that's an example of something where the limit doesn't exist. Because if you think about it, if the limit exists, then that means eventually when you get close enough to x equals 5, the y value should be pretty much close to some, it should have pretty much decided where it's going to go. So like, you know, if you're going, for instance, if you're going this direction, you know, the y value is jumping up and down, but if you're looking at the limit as you go towards x equals 2, eventually when you get close enough to x equals 2, the y value sort of decides where it wants to be. It decides it's going to settle on y equals 2. But if you're going this other way, and x is getting closer and closer to 5, instead of the y value sort of settling down and deciding where it wants to go, it's just getting more and more frantic and more indecisive. And so since it never really settles down and starts, you know, really pointing towards one point that it's going to, we say the limit does not exist from the left. So that's sort of a long, drawn-out pictorial explanation of why this thing is that does not exist. Okay? All right. So this is just sort of a problem that illustrates a bunch of different ways that limits can behave. The very last part that we were just talking about is probably about as complicated as these limit problems are ever going to get. It's pretty complicated looking, but it's sort of a nice problem that sort of illustrates almost all the different types of limit situations that you're going to encounter.